Hello everyone, my name is Diego and this work is related to my PhD thesis that deals with navigation of wheeled robots in rough terrain. My objective here is to present you a torque optimization based on multi-objective and genetic algorithm, also to develop a strategy to provide real-time control. Our focus is in the application of mobile robots with few degrees of freedom in challenging terrain. We also consider that the robot has to overcome obstacles on its trajectory. Thus, our approach is based on stability control. In this work, a two-dimensional quasi-static model is used to simplify the control of four-wheel drive robots. We have four variables to satisfy three equations, so in this situation, an optimization process can be applied. Our first objective here is to maintain a minimal stability margin during the robot movement. The second objective is to maintain the relation between traction force and normal force as minimal as possible to guarantee a minimal wheel slip. In our optimization, each torque is considered an individual of a genetic algorithm, and the robot electrical and mechanical features are the restrictions. Solutions obtained for multi-objective problems using genetic algorithms usually are accurate, but they are also slow. In our work, we consider there is a relation between the robot state and the torque necessary on each wheel. Simulations using two robots show that a decimal order polynomial describes this relation. In this figure, we see Puma Plus, a high-torque mobile robot developed at our lab and used in this work. Here we can see an optimal solution for Puma Plus, considering different robot inclinations. The values shown in this figure are for a friction coefficient of 0.5. For general solutions, a zone of possible torques can be obtained around the curves shown in this figure. Here we have an experiment using a generalization of our algorithm. The Puma Plus robot climbs a step in less than 3 seconds. The robot accomplishes its trajectory using a PID low-level torque control and our optimization as its high-level control. It's important to note that the Puma Plus robot was not able to perform this movement in radio-controlled or velocity-controlled modes. Also, during the trajectory, it's possible to observe that the torque never exceeds an established threshold. A second experiment is performed in this work using the bot-kit robot and a high inclination slope. In this case, we make another generalization, useful for velocity-controlled robots. We have here a velocity control using torque feedback. So, again, the developed algorithm is used to find a set of torques where the robot performs an aligned trajectory predicting its real torque. Here, the bot-kit robot is in a slope with 46 degrees of inclination. On the first situation, we don't have any type of optimization. On the second situation, we have a velocity optimization. On the third situation, we have a velocity control with torque feedback using the sensor installed above the robot. As you can see, the robot can perform the desired movement only on the third situation using our algorithm. More, in this test, the orientation of the robot is not controlled, so only the stability problem is evaluated. Finally, it's noticed that the technique is suitable for general-purpose robots with four-wheel drive systems. It can be used in diverse terrains, and the only condition is that the wheels have to maintain a contact with the ground. A three-dimensional algorithm also will be developed to improve the method's applicability. We would like to acknowledge NVIDIA and CNPq for their contribution for this work. Thanks so much for your attention, and if you have any question, please contact me.